Hey guys, we're going to work through a practice problem of an object on an inclined plane today. So here's our prompt. We have a 1,000 kilogram roller coaster traveling on an incline of 30 degrees. We have to draw the free body diagram, determine the net force in the x direction, and the acceleration of the roller coaster car. Ignore friction and air resistance. So over here I'm going to draw my incline first, and I'm going to indicate my 30-degree angle. And because I'm very artistic, our roller coaster car is going to be a square. So free body diagram, law of free body diagrams. Gravity always points directly down. Let's pretend that is more directly down than it is. Our normal force always is perpendicular to the surface. So that is our Fn. Now that we are on an inclined plane, our Fn and our Fg are no longer the same thing. And we want to add our forces in the x direction, so what we have to do is actually break apart this Fg vector. Since this is technically at an angle, we want to break it apart into two legs of a triangle. So the first thing I'm going to do is extend a blue dotted line this way, and this is my Fgy, or my y component of gravity, and then I'm going to connect that triangle to make my Fgx, which is my x component of gravity. So here we have our free body diagram, and the last thing that I want to add is this inside angle right here. That is the same as this angle. There's a mathematical theorem that states that they are the same. I just expect you to know that they are the same. So our 30-degree angle of the incline is the same as the angle in between the hypotenuse and the Fgy. So there's our free body diagram. Our first part of the problem is done. Our second part of the problem, determine the net force in the x direction and the acceleration of the roller coaster. So in order to determine Fgx, if we use this inside angle right here, x is actually the opposite side. So we are going to use Fg sine theta, since that green line is opposite the angle we know. If we were looking for Fgy, we would be using Fg cosine theta. So Fgx is mass times gravity times sine theta. We plug in our unknowns. So Fgx is 1,000 times 9.8 times sine 30. And when we plug that into our calculator, we come out with 4,900 newtons. Now if we look at our picture, we have two arrows going in the y direction, Fn and Fgy, because remember, breaking apart this puts this in a new perspective for us. So it's like we could just tilt that incline and making that 30-degree angle a flat surface. And we only have one arrow acting in the Fgx or the Fx direction. So when we do Fnet in the x direction, the only arrow we have to take into consideration is Fgx. And every time we see an Fnet, every single time, we can replace it with an m times a. But specifically, since there is an x here, we have to indicate the acceleration in the x direction only, and that is equal to what we solved for over here of the 4,900 newtons. So again, our mass is 1,000, our a is unknown, and our Fgx is 4,900. At this point, all we have to do is divide out the mass. And when we divide out the mass, we are left with an acceleration in the x direction of 4.9 meters per second squared. Now, if we go back to this first equation, right here, this Fnet equation, we could have adjusted that to include friction. And if we did, the only thing that would have changed is here we would have had minus an FF, which we then could have substituted our mu Fn, which is our mu Fgy, now that we are on an incline. Fn used to be equal to mg, but it is no longer. It is equal to the y component of gravity. But again, this wasn't an issue in this problem. They didn't ask for it. I just wanted you to know that that is a possibility that we could take it into consideration. Hopefully this helped you guys out, and we will see you guys later.